Moving to section 7-3, we're looking at entropy change of pure substances. So you probably already saw from those property tables that entropy was a property on those tables, and so we can find the entropies for certain substances at certain temperatures, at certain pressures, and it's just like all those other properties. So you already know this, but if it's a compressed liquid, if we have a compressed liquid table, we can use that, or we can just usually assume that the entropy is approximately equal to the entropy of the saturated liquid at that temperature. If we're told it's a saturated liquid, we just look at the SF value. If we're told it's a saturated, down here, saturated vapor, we look at the SG value. If it's a mixture, we kind of need to know the quality. We'll take the saturated liquid value plus the quality times the difference in liquid and vapor, SFG. And if it's superheated, go to the superheated tables, superheated vapor tables, in order to find those entropy values. If we're looking at capital S, take the mass times S2 minus S1. If we're looking at the entropy change, it's m dot delta S. But you already know, I think, most of these, how to use these property tables. So we can use property tables in order to find the entropy at the initial state, the entropy at the final state. There we have the change in entropy right there. So let's look at some problems. Problem number 5, we've got a rigid tank, has 5 kilograms, refrigerant 134A, initially at 20 degrees C and 140 kPa. The refrigerant is now cooled while being stirred until its pressure drops to 100 kPa. Determine the entropy change of the refrigerant during this process. So we want the entropy change. We want S2 minus S1. So let's kind of think about state 1. State 1, 20 degrees C, 140 kPa. That's two properties right there. From that, we can go to our refrigerant table, and from that we can find the S1. All right, so pause this, go to the refrigerant table, see if you can find S1. I got S1 is 1.0625 kilojoules per kilogram K. This was superheated. So first I went to the property table, but then I saw that the temperature was too high for that saturation pressure, so I knew it was superheated. Went to superheated vapor table, found the S1. Now, for state 2, so there I've got S1, awesome. For state 2, what do I know about state 2? It's cooled while being stirred. Its pressure drops, so its pressure is 100 kPa. What else am I told? What else do I know? It's a rigid tank. So the volume stays the same, and the specific volume stays the same. If I could find little v, lowercase v1, specific volume initially, that would be the same as the specific volume final. So I go back to this same superheated table. I go back to that table. Use these property tables, and please do this with me. Have your property tables beside you. Take the time to find these properties. Be comfortable with that. All right. So I've got the specific volume was 0.16544 meters cubed per kilogram. So that it is still, the specific volume is still 0.16544 meters cubed per kilogram. So now take these two pieces of information, see if I can take these two pieces of information and find the entropy. So where if I look at this saturation pressure, I would find that this specific volume is in between VF and VG. So this is a mixture. This is a mixture. So first I'm going to solve for quality. I'm going to solve for quality. Then if I know quality, then I can find the entropy. All right, so looking at this V, this 0.16544, the VF, right? V is VF plus X VFG. The VF is 0.0007258 plus quality is what I'm looking for, 0.18255 minus 0.00072. I put one too many zeros right there. 0.0007258, and there I can get the quality 0.859, and I can use that for entropy. So entropy, same equation. S that I'm looking for equals SF plus X SFG. So going to the mixture table for refrigerant at that pressure, is that table A11 or A13, whichever one is the pressure table. Then let's see, I would get S that I'm looking for is 0.07182 plus the quality 0.859 times 0.88008. I would get the entropy 2 is 0.8278 kilojoules per kilogram K. Alright, so the change in entropy. If I just take this S1 and S2, that's actually the change in specific entropy. So to be completely correct, let me take delta S is the mass times delta little s. So delta S would be 5 kilograms times 0.8278 kilojoules per kilogram K minus 1.0625 kilojoules per kilogram K. And so delta S is negative 1.173 kilojoules per K. Is it okay that it is negative? Yes, because that is just the entropy change of the refrigerant. We didn't look at its surroundings. Also, it wasn't isolated. You know, it was being cooled. You know, so there was some heat loss. It was being stirred. You know, there are things crossing work and energy crossing the boundaries. So it's okay if the entropy in something is negative. It's only when we're looking at the total entropy of everything when it should be positive. Okay, let's look at the next one. Piston cylinder device initially contains 3 pounds of liquid water at 20 psi and 70 degrees Fahrenheit. The water is now heated at constant pressure by the addition of 3450 BTUs of heat. Determine the entropy change of the water during this process. Alright, so we've got this piston cylinder device. It's a piston cylinder, and it said it was a constant pressure device. We're adding 3450 BTUs of heat. We want to know the entropy change of the substance. Alright, so let's kind of look at state 1. It was at 20 psi and 70 degrees Fahrenheit. Alright, so from those two pieces of information and the fact that it was water, I would go to the water table, table A4 or A5, and I would see that actually it's not on A4 or A5. It is a supercooled liquid. And so if I have a compressed liquid, I could try to go to compressed liquid table if I have that pressure and temperature. Or I could say, you know, the SF at 70 degrees Fahrenheit. So I'd go to the water temperature table. At 70 degrees Fahrenheit is 0.07459 BTU per pound mass Rankine. All right, so that's the S. Let me try to find the S final. And this is going to be a little bit harder than we might think. All right, so I know that it was constant pressure, so I know it's at 20 psia. But I don't know any other information. I really need two pieces of information to, you know, to fix the state, to find everything else. So I need to find one other piece of information, and then I can find the entropy. Okay, so what do I know? I know I've got this Q. And that Q is this is not an isothermal process, but this is like those what we did in chapter 4. Let's look at conservation of energy, and let's see what we can do. Q plus W, there's no mass going in or out, equals delta, you know, well, should I do delta U or delta H? Well, if I include the boundary work, so boundary work is if I include boundary work and delta U, then that right hand side is delta H, and it's good and it's okay to use delta H for a constant pressure process that has boundary work. So then I've got my boundary work. So Q is delta H, and we're given Q, we know Q, so we could find delta H, and delta H is, you know, H2 minus H1. I bet we could figure out H1. Let's get H1. All right, so let's get H1. Assuming it's a compressed liquid, so we can take the value for the saturated liquid at 70 degrees Fahrenheit. This is 38.08 BTUs per pound mass. All right, so I've got this equation. Q equals delta H. Delta H is M times little h, 2 minus little h1, and I have all of these values except for h2, which I can solve for. All right, so 3450 BTUs, and that's a Qn, right? So it's a positive Q, equals 3 pound mass. Let's be careful with my units, make sure it works out. H2 that I'm looking for minus 38.08 BTU per pound mass, and oh, well, units work out perfectly. I've got an H2 of 1188.1 BTU per pound mass. All right, so now I know that H2 is 1188.1 BTU per pound mass. I can take these two pieces of information, that fixes the state. I can find anything else I want to. So from this, I would go to my property tables. So pause that, go there right now, see if you can find the S value. See if you can find the S value at this pressure and that enthalpy H. All right. I've got to interpolate, and this is what I calculated. I've got S2 is 1.7761 BTU per pound mass Rankine. Now I can tell you the entropy change. If it's asked for entropy change, I'm going to assume total entropy, not specific entropy. So capital H is mass times capital S equals mass times little change in entropy. Change in specific entropy, 3 pound mass times 1.7761 BTU per pound mass Rankine minus 0.07459 BTU per pound mass Rankine. and I would get change in entropy is 5.105 BTUs per Rankine. And this last problem on entropy changes of pure substances. All right, got refrigerant 134A at 320 kPa and 40 degrees Celsius undergoes an isothermal process in a closed system until its quality is at 45%. On a per unit mass basis, determine how much work, lowercase w, per unit mass, and how much Q are required. Okay. All right, let me just start kind of looking at initially. Initially, it's at 320 kPa. The temperature's at 40 degrees C. And final, it underwent an isothermal process, so it's still at 40 degrees C. And its quality is 45%. So, this is two pieces of information. I could find anything else I wanted to. If I needed to find entropy, S1. If I needed to find maybe U, maybe H, or whatever I needed to find, I could find. Same thing with once I know this is this temperature, and I know it's a mixture because it gives me a quality, and I know that quality, so then I could go to this, make sure you go to the right table for refrigerant, go to the temperature table, and if its quality is 0.45, I could find S2, I could find U, I could find anything. I'm not really sure actually just yet what I need to find, but I could find any of those values. So if it asks for, the change in entropy, I could tell you that. But it doesn't ask, it asks for the work per unit mass and the Q per unit mass. All right, so let's kind of go back to our conservation of energy. Q plus W equals M. Is this going to be a delta U or a delta H? Well, it doesn't tell me what really type of process. It didn't say rigid tank. It didn't say constant pressure. So I'm going to need to do the delta U, and I might have to calculate boundary work. So this is one of those where it's not necessarily constant volume, not necessarily constant pressure. So we got to use Q plus W equals M delta U. Now, let's think about this. I don't know this, and I don't know this. I do know that. I think I could find my delta U. So I can't use that equation by itself. All right, let's think about this heat transfer. We have heat transfer in an isothermal process. The Q for an isothermal process, well, the delta S is Q over T. And we know the delta S, or we could figure it out. We could find it. We know the T. That's how we're going to find Q. I'm going to find Q by delta S times temperature, or little q. These should really all be per unit mass. Let's rewrite this as Q plus W equals delta U. Q is lowercase s times T. All right, so let's find the S. So let's find all of these values. And actually, I think you can see we're not going to use H for this. We might use U. So pause this right now. Make sure you can find S1 and U1. Make sure you can find S2 and U2. All right, I'll write what I've got. I got S1 is 1.0432. That would be kilojoules per kilogram K. And U1, 261.62 kilojoules per per kilogram. I got S2 is 0.69 or 6292 kilojoules per kilogram. Okay, and U2 172.02 kilojoules per kilogram. All right. So I'm going to calculate the Q not by conservation of energy, but from entropy. Q is delta S times T. I could only do that because it was an isothermal heat transfer. All right, so Q is S2.6292. I should keep up with my units, but I'm going to leave those out. 1.0432 times the temperature, 40 degrees C, but I've got to have this in absolute temperature. Sometimes you can get away with leaving it in Celsius if this was a delta T, but if it's just a T, like PV equals RT, or Q over T, if it's just a T, that almost always needs to be absolute temperature. So I changed that, and my units, everything works out. Q is negative 130.2 kilojoules per kilogram. All right, so there was some heat loss, and that's fine. Now it asks for the work, so now we can go back to our conservation of energy equation. Q plus W equals U2 minus U1, negative 130.2 kilojoules per kilogram, plus any work. Could be boundary work, could be, external work, just any work, equals, let's see, U2, 172.02 minus U1, 261.62. The units do work out. The work, lowercase, would be positive 40.6 kilojoules per kilogram. 40.6 kilojoules per kilogram.